Strokes are the 10th leading cause of disability-adjusted life years, which are the number of years lost to health, disability, or early death. A 2017 study from the Heart and Stroke Foundation reports that 400,000 Canadians are living with the effects of a stroke. As a matter of fact, 60% of stroke survivors suffer from persistent neurological deficits that impair activities of daily living. The team at Rehabilitation seeks to target upper extremity hemiplegic stroke victims in our design. These victims suffer from a deficit known as hemiplegia, which is, to put it simply, the unilateral paralysis of the body. Commonly today, we find that upper extremity hemiplegia stroke victims rehabilitate using mirror therapy technology, paired with physiotherapy, of course. This form of rehabilitation, while effective, does not, however, induce total recovery of limb movement, which leaves patients with repercussions left over from social impacts left behind by the stroke. According to the Health and Stroke Foundation, studies have found that a significant number of mild stroke patients experience challenges around mobility, relationships, work, and recreation up to a year after stroke, yet the majority indicated receiving little in the way of post-stroke rehabilitation. Previous iterations of similar designs came in the form of physiotherapy robotics, assistive devices, haptic devices, and master devices. These were meant to enhance the results of mirror therapy, as mirror therapy rehabilitation does not induce total recovery for patients. Patients who undergo only mirror therapy do not regain full control of their limbs. Dr. Hussain from the University of Guelph proved that robotics provide more favorable results when used for rehabilitation. An example of one iteration of our design is an exoskeleton glove meant to amplify the grip strength of the hand. For the current scope of our project, we intend to present a design which targets patients experiencing upper extremity hemiplegia. This design will provide full mobility during a variety of activities and aid preventing atrophy during mid-stages of recovery.
The exosleeve was chosen over the other designs based off the following constraints and criteria. The design must be under the budget of $48,442.97. Those costs are based off of OSPE, and the overhead costs are included. The design must be completed by the date of the final design report, which is on April 6, 2020, and the design must allow for use at home. This was important because the idea is to give the patient the freedom to move around and perform daily tasks, so a mobile design was a key component. The design must support arm and hand movement. The idea of this was that they need to have their arm and hands supported because that's the affected region where the paralysis is, and we want to help them rehabilitate and improve motor function. And now some following criteria that we're trying to aim for. We want to minimize weight. This will help prevent muscle fatigue, allow for longer periods of use. Ease of use. This can be measured by how easily the patient can learn the device. If it only requires one introduction, it can be considered easy. Again, we want to minimize power consumption because this will lower the cost of powering the device as well as affect how long it can last. And improve muscle condition of hemiplegia patients. Improving the muscle condition of the patient is the aim of the device. Help rehabilitate the muscles and nerves back into working order, and this can be measured based off the data of how it helps patients. And again, another really important criteria is to minimize the possibility of injury. This was done by ensuring the design was lightweight and strong enough to survive fall, so it doesn't affect the patient.
When generating a potential solution, it was important to first assess the strengths and weaknesses of manual assisted therapy. Thereafter, we were able to use MATLAB and SolidWorks software, as well as Google Patents, to assess existing solutions and their respective limitations. Taking this into consideration, 3 ideas were generated. The following pictures depicts 3 of the top iterations for this design process. The following diagram depicts the design process evaluation model associated with this solution. To evaluate these alternatives, a Pew matrix was used to compare and scale various criteria in order to obtain a weight factor for each respective criteria. Using these weightings, we were able to construct a decision matrix to evaluate each design by assigning a mark for each corresponding criteria. By observing the table, as can be seen, the exosleeve achieved the highest value. Finally, the decision matrix was scaled accordingly to meet the considerations of the government and patient. For the government scheme, weight was added to the environmental impact, whereas for the patient scheme, additional weight was added to the user cost and mobility. In both cases, the exosleeve had a significantly higher value with respect to the other two alternatives. The exosleeve would be the first and only solution that would provide rehabilitation to the arm and hand while also being a portable design. This allows the user the freedom to use it in multiple settings and in a variety of functions to ultimately maximize their functional independence.
So our team decided on the exosleeve as the optimal design solution. We did modify it a bit after by adding the vest so that the user is better able to support the weight of the device, and we changed the material of the vest from ABS plastic to Kevlar since it's lighter. At the arm, instead of solid beams, we put 2 thinner beams in each section to reduce the metal there by a third, and we changed the ball joints at the elbow and the wrist to hinge joints because they're more feasible. The sleeve itself is made of microfiber because it's durable, strong, comfortable, and breathable. And then underneath this is the exoskeleton. So for the joints we use stainless steel because it has a high compressive strength, and this is because we needed to be able to support large forces acting downwards, for example from the weight of the user and the other components. And then the beams supporting the upper arm and the forearm are made of carbon fiber because it has a high ultimate tensile strength that will allow it to be able to withstand impact force, for example from a fall, without breaking and injuring the user, and it has a low weight that reduces the stress on the motors and the patient's body. So how it works is that electromyogram technology, known as EMG, will detect impulse responses from the user and send a signal to the exoskeleton so that it can act accordingly. And we use an Arduino to integrate the EMG with the exosleeve, so the user will have to calibrate the device at their max and min signal responses, and the program will monitor for EMG signals produced by the user and their intensity, compare it back to the calibrated signals to control the speed of the motor's output, and then the motors will carry it out by applying a force on the exoskeleton.
Expanding upon this further, we were able to address the technical aspects of the design. This first design iteration considers the human anatomy and measurements of a 40-year-old man. These measurements allowed us to compute the maximum torque and motor requirements to ultimately determine the optimal mechanical system. That said, it was determined that 2 12-volt motors would be required for the shoulder, with an additional 2 motors for the elbow and hand component. With this in mind, an electric motor was selected for exoskeleton actuation due to its optimal position-based controller, specifically the brushless DC motor for its high torque-weight ratio, which means that it has an increased efficiency. In order for the design to be fully autonomous, the battery must supply enough energy to support these actuators. It should also be cost-effective to meet the project budget. In addition, the battery must be portable and rechargeable, as well as being relatively lightweight to maximize mobility. Based on these factors, lithium-ion batteries were determined to be the most valuable options. Not only do they meet the power requirements, they have a relatively high energy density while also being lightweight, cheap, and providing 99% charge efficiency. To ensure that the safety of the user isn't compromised, all aspects of the design were chosen under consideration of set exoskeleton guidelines and Canada's Occupational Health and Safety Regulation. It was important to first determine the factor of safety to ensure the reliability of the design. This was calculated to be greater than 33,000, meaning it will not fatigue unless damaged, resulting in an increased life cycle. Secondly, since the exoskeleton is relatively close to the skin, it was important to perform a full heat generation analysis on the battery. Optimal operating temperatures would be 37 degrees, which is the core temperature of the human body. Taking into account any additional heat through charging and discharging, the peak operating temperature was determined to be 41.78 degrees Celsius. Although this temperature is slightly above the desired temperature, the exoskeleton is not in direct contact with the skin. Furthermore, the carbon fiber build acts as an insulator because of its high heat tolerance.
To continue, some of our assumptions do add an element of risk to the design, and so that's what I'll be talking about here. So to start off, we wanted to make sure that a lot of different patients can use our product, so we based our calculations on upper extremes because they would generally imply that it would also work for lower values as well. But in certain cases, this creates uncertainty and risk because sometimes it's better to look at the lower extremes, for example, certain safety calculations. An example would be if we are trying to figure out the maximum weight that the device can be for the patient to be able to comfortably wear it. If we use like the upper extreme values, it might not work for the lower values because it might end up too heavy in that case. And other factors that add risk include environmental temperature wherever the device is being used, because that is pretty unpredictable at the end of the day, regardless of whether or not we release it in a specific region. And also there would be inevitable imperfections in the material that we just can't avoid sometimes, even if quality control is in place.
Overall, the social benefit of the exosleeve is a positive one. It improves the social benefit to the community by allowing improved happiness of acquaintances who know the hemiplegia patient by knowing that the device is helping their quality of life and their well-being. There is a social benefit to allowing the user to wander around in public. It allows regained motor function of the hand and the arm, which can be quite nice when you're wandering around in public. And then there is a social benefit to the home life, and this is in the form of allowing the user to perform daily tasks, such as getting a glass of water or moving things around in general.
The chart provided in the slide showcases the CO2 equivalent emission for each material used in the exoskeleton. It's important to note that these materials are based off of the average proportions of a 40-year-old male and will vary depending on the customer. 1 megajoule of electricity was found to emit approximately 234.8 grams of CO2, and using this conversion factor, the total CO2 equivalent for the materials of one exoskeleton unit was estimated to be about 308,973 grams. For the end of the product life, the ABS plastic and carbon fiber materials can be disposed of via landfill, while the stainless steel components can be recycled. The lithium-ion batteries, however, can be recycled through companies such as Green Tech. The top chart in this slide showcases the material cost used for the production of a single exoskeleton unit, as well as the companies where these materials will be sourced. Total costs for the materials were calculated to be $1,846.29. The bottom chart lists all of the additional costs during the production of the exosleeve. There was a labor cost of $42,170, which was derived from the OSP guideline, and an overhead cost of $6,272.97. as well as a non-provisional patent cost of $14,000. This totals to $64,289.26, with an estimated variable cost of $300 depending on the dimensions of the customer. By the end of the year, our company intends to sell 18 units to the surrounding physiotherapy clinics, and we intend to sell one exosleeve unit for $31,000 and estimate a profit of about $310,200 calculated using the previously mentioned costs and sales price. There aren't many economic impacts regarding our product, however we do provide a cheaper alternative to other exoskeletons, which can average to be about $45,000 per unit, as well as providing many jobs in our company for upcoming engineers and computer scientists alike.
Rehabilitech is committed to the continued research in this field of technology to develop appropriate solutions to the hemiplegia patients today that can be cross-applied to other disabilities in the future. Our goal is to improve the future of those with disabilities by reducing physical, financial, and systemic barriers. We hope to create a future with more easily accessible services and support for all who have a medical disability affecting their daily life. Our vision is to always reach the golden standard with all technology developed.